So here we go. Let's take a tour, a quick tour of the periodic table, because by the end of this tour, we should be able to pretty much know all the different parts of the periodic table. So when I say the lanthanides, your eyes should be able to go directly to the lanthanide series. All right. What are horizontal rows? What are they called on the periodic table? Anyone remember from middle school?
Horizontal.
Jeffrey. What? No, they're not called groups.
Columns.
They're called periods. Periods. How many horizontal rows are there on the periodic table?
9.
No.
8.
No.
10.
No.
11.
7. Okay, why are they not 9? Because if you look and see the bottom two what you would call periods or rows are actually inside of number 6 and number 7. We call them the inner transition metals because they're inside of those.
Ooh.
So I can understand you saying 9, but in reality it's only 7. How are they designated? Quite simply, look on the left. A number. Okay? A number. Period 1, period 2, period 3, period 4, period 5, period 6, period 7. Now, folks, it's not a coincidence that's called the periodic table and that it acts like a calendar. Okay? For reasons that ladies understand and guys don't, okay, it is not a coincidence that for a young lady or even an older lady, the word period means something to them. Because there is a pattern that a young lady's month follows. Okay, I'm trying to be as delicate as possible in order to help you guys understand that the periodic table works the same way. Okay, the young ladies follow a certain pattern through the calendar. Okay? A repeatable pattern. In the same way, the periodic table will also follow a pattern. Our job is to try to understand that pattern, because once we understand that pattern, then we can look anywhere on that periodic table and be able to come up with the properties of the elements that live in that part of the periodic table. Just like a young lady, you can point, you don't want to do this if you're a guy, but they can point to any day on their calendar and they can tell you pretty much how they're going to be feeling on that day. Okay? Same principle. It's not a coincidence. It's called the periodic table. Okay? Because that word means the same thing in both hemispheres. What are vertical columns called? They're called groups or families. Groups or families. Groups or families. How are they designated? How are they named? Now, in your periodic table, they may have like a 1A or 1B or 2B. That's terribly disappointing. That's very, very confusing. So the best way to designate them is by using either a name that is used to describe the whole family, or by using the first name of the element on that column. For example, the lithium group is also known as the alkali group. The beryllium group, that is also known as the alkaline. Now, I will apologize, even though it's not my fault. I didn't name these things, Kelsey. That alkali and alkaline sound so familiar. I think it's so not fair. Okay, alkali sounds like the singular version of alkaline, doesn't it? But they are two very distinct types of metals with different properties. No, the zigzag line is not there. The zigzag line is on the right side. We're talking about the first two columns. Okay? The next to the last column is the fluorine group. And they are called the halogens. the halogens. So all of these guys with special names, you must learn those special names. Because from now on, I may refer to them as the halogens, and you need to be able to know exactly where to go on the periodic table to find the halogens. Finally, the helium group has a special name, and that's called the noble gases. And they do not react with anything. They do not react with anything. I like to think of them as the nuns of the periodic table, in that they are female, but they don't get married. They do not interact with anybody. They are happy just the way they are. What is the periodic law? There's a certain law that explains this whole thing, and this is it. It's similar to the one that Dmitri Mendeleev came up with, but in his time there weren't any protons. So he didn't know anything about atomic numbers. So his periodic law involved atomic masses, but it didn't work perfectly. It wasn't until protons were discovered that they were able to alter this periodic law, and it makes sense. When you order the elements according to increasing atomic number, or the number of protons, the chemical and physical properties will repeat themselves. Has anyone ever typed on a typewriter?
Yeah.
Okay. They are cool because you go a certain distance and then there's a little bell that goes off, which means you need to scroll back. In the same way, the periodic table works the same way. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, ding, scroll back. And I can go this way. Very reactive, not as reactive, still metallic. Now somewhat metallic, somewhat non-metallic. Non-metallic can react 4 times. Nitrogen is a gas, can react 3 times. Oxygen reacts 2 times. Fluorine reacts once. Neon doesn't react at all. Ding! Go back to the beginning. Sodium reacts 1 time. Magnesium reacts twice. Aluminum reacts 3 times. Silicon 4. Phosphorus 3. Sulfur 2. Chlorine 1. Argon. Ding! Go back to the beginning. Constant patterns that repeat themselves, but it only works if you put them in increasing atomic number. Let's have Hank Green explain this to you.
The different groups Mendeleev had identified are a lot of the same groups that we study today. Starting at the left, we have the soft, shiny, extremely reactive alkali metals, so reactive, in fact, that they have to be stored in inert gases or oil to prevent them from reacting with the atmosphere. Alkali metals want nothing more than to dump off an electron and form a positive ion or cation, and they're always jonesing to hook up with a hottie from the other side of the table. So, of course, seeing as they're so reactive, you don't find hunks of them lying around in nature. Instead, chemists must extract them from compounds containing them. Next, you have the alkaline earth metals, reactive metals, but not as reactive as the alkali metals, forming cations with 2 positive charges instead of just 1. Calcium, shown here, undergoes a very similar reaction to sodium and water, just a little more slowly, producing a little less heat. The middle body area of the table is made up of a nice solid rectangle of transition metals. These are the metals you think of as metals, with iron and nickel and gold and platinum. The majority of elements are metals. They're fairly unreactive, great conductors of heat, but more importantly for us, good conductors of electricity. They're malleable and can be bent and formed and hammered into sheets, and they're extremely important in chemistry, but overall surprisingly similar to each other. On the far right, just over from the noble gases, the halogens make up a set of extremely reactive gases that form negative ions, or anions with 1 negative charge, and love to react with the alkali and alkaline earth metals. The rectangle between the halogens and the transition metals contain a peculiar scattershot of metals, metalloids, gases, and nonmetals. These guys don't end up as ions unless you take extreme action and start shooting other ions at them, so generally a bit boring over here, though lots of interesting covalent organic chemistry. We'll get to that. Down below, in their own little island, are the lanthanides and actinides, metals that were largely undiscovered in Mendeleev's day because they're so similar that it's next to impossible to separate them from each other. And finally, on the far, far right, also undiscovered when Mendeleev built his chart, the completely unreactive noble gases. Like our periodic table as it stands is really a little bit unhappy with itself, frankly. The lanthanides and actinides really should be be part of the table, but we separate them out because it's hard to fit that on a piece of paper. Really, this is what it should look like. And really, it would be best if it wrapped around into a circle so that fluorine and neon and sodium were all next to each other instead of being on the opposite sides of the map, because they're just one proton away.
All right. So let's take it apart piece by piece, and let's name all the different parts. First column. Let me get some black ink. Alkali. Very reactive, desperately wants to give away one electron. So dangerous that if you come in contact with it, it'll give you an electron. Actually, by giving you an electron, it converts water, which you're mostly made up of, into hydrogen gas. That hydrogen gas is what they use in rocket fuel, and that hydrogen gas, with just a little bit of heat, will explode, blowing your mouth out if you try to take a piece of it into your mouth with teeth and tongue and all that stuff. Yum, yum, yum. Don't mess with alkaline. Alkaline is right next to it. You probably are familiar with them because you've heard of alkaline batteries. Okay, many alkaline batteries will have a paste in them that's made up of an alkaline metal. This middle section is called the transition metals, and they're made up of metals that are pretty much the same characteristics, same properties. Very malleable, as Hank said. Ductile, will conduct electricity well. Then over here, totally inert, not interested in anything or anybody, are the noble gases. Next to them are the halogens. Just like the alkali were very, very dangerous to us, and the alkaline to a smaller extent. The halogens are very dangerous in that they want to take away an electron. And once again, when they take away electrons from us, they change who we are. And that's not a good. Well, no, but they will poison you and kill you, and not even slowly, necessarily. All right, over here is a section that's been ripped away from the transition metals. Actually, if it hadn't been ripped away, then we would have had to have moved these last two groups, 14 elements, over to the right, and would have messed up the whole patterns thing that I was talking to you guys about. Totally have messed it up for the last two, including the fact that, the periodic table over here would have extended past our beautiful little rectangle and mess everything up. So, Glenn Seaborg, an actual Oak Ridger, okay, he lived over there in New York Avenue. He was the first one to say, hey, let's start putting these guys down here. So, yes, really, he discovered several, not discovered, yeah, he kind of discovered or created several of the elements. Actually, can Knoxville say that they have a former citizen on the periodic table? Look at element, I think it's 106, SG. Seaborgium is named after an Oak Ridge resident. Seaborgium. Okay, so he's the first one that said, hey, let's put these guys down here. This is called the lanthanide series. Lanthanide. And the actinide. And Ben, this is why we don't have 9 periods, because these guys are actually inside the transition. These are called the inner transition metals.
Wait, how do you say the bottom one?
The lanthanide and actinide are called the inner transition metals. Together, these first two and the last 6 are called the representative elements. The first 2 and the last 6 are called the representative elements. And do not forget the zigzag line, Nicole, which is over here. And on either side, you have the metalloids. On either side, you have the metalloids. All right, we've taken a tour of the periodic table, so now we should know at least where all the different parts of it. Maybe not understand why they are where they are. That's next.